Alright, I'm gonna record another video for 114. First of all, as I said, when we introduced the theory to find the magnetic force on a moving charge, what did we do? Was this, right? So that's the theory to find the magnetic force on a moving charge. And I said there is a way to test this theory, right? Well, this is very non-intuitive to everyone, right? As I said, the first time I learned this, it was like really weird to me, right? How come the force, it's gonna be so weird that it's gonna be perpendicular to the velocity, perpendicular to the b, right? So, as I said, there's a way. So how do I believe the theory, right? Do an experiment and then test the theory, right? So, as I said, there is a way to test the theory, but I can't grab a charge, a single charge, and then have the charge move in the magnetic field and then show you it's going to be deflected this way, that way. But what we learned is this: if this is true, then if you apply this theory to the conductor, which carries current, then this a straight current. So this conductor is going to feel a force, which is going to be the sum of all these forces on these little moving charges in this conductor, right? And this is very easy to verify. But remember, this is a conclusion from that equation, right? So this is a conclusion from that equation. So by verifying this, I can verify this theory, right? And this is very easy to set up. All you need to do is just use some magnets to create a magnetic field, and then set up a current. And current is easy to set up. You just connect the conductor to a battery, then there's a current. And then put the current inside the magnetic field. Then you can see if there's a force. There is a force from the magnetic field on this current. And does that agree with this theory, right, with the right-hand rule? Okay, so that's what I want to show you in this video at the beginning. Okay. So Eric German set this up for me. Yeah, everyone's working now. So this guy, you see, I hope you can see this very clear. I have this rectangle loop, okay, inside this magnetic field. So there are two magnets here, very close, right? This is one, this is another one. I think this pole is a north pole, this is south. And then this pole is the south pole, this is north. So the magnetic field between this and this gap is going to be down, right? Because this is the north pole, this is the south pole. So we will have magnetic field down in this gap. Now, what about the current, right? So now, and then this loop is connected to these two wires, and these two wires are connected to voltage source, right? So if I turn this on, so the white one, the white wire is connected to the positive terminal, and the purple one is connected to the negative terminal. So if I turn this on, the current is going to go to this through this white wire and go to this loop, and then go back to the purple wire, and then go back to the negative terminal. So, so there, inside this magnetic field, there must be a current coming this way, so toward me, right? So if I draw it out, it's going to be, I set up a current into the page, right? This current goes this way, white wire goes down, comes back, and the purple wire and goes back to the terminal. So then, if you use this theory, what will be the direction of the force on it if I turn it on, right? So you would do I toward B, right? So you're going to do I into the page, right hand, B down. So if this theory is true, then this guy, this loop, it's going to feel a force to your left, right? Okay, so that means that if I turn it on, there's a current in this loop, then you will see the loop actually moves in that direction. So move to the left, okay? So should see the loop in that direction, okay? So I'm going to turn it on, okay? And now it's free. right, in this region, no force on it. But if I turn it on now, I'm gonna first stop it. Right? Hope you can see that. When I turn it on, it does feel a force in that direction, pushes in that direction. That's from the magnetic field. Okay? Okay, I turn it off, the force disappears, it comes back. And then another thing we can do is that, what if I switch, what if I reverse the direction of the current, right? So, and that's easy to do, right? All I need to do is just switch these two connectors, right? So if I switch these two connectors, the magnetic field is still down, right? I didn't do anything with the magnetic field. Now if I turn this on, the white wire, remember, it's connected to the positive terminal, so you're going to see a current going this way, down, and then toward you, and comes back. So in this case, the current is going to be, if I draw it on this board, it's going to be out of the page, right? So in this segment, the current is going to go that way. Then what is going to be the force on it? You're going to still do right-hand rule, right? So you're going to do current out of the page and curl your forefingers down. So it's going to be hard to do. Out of the page, down, so your thumb is to the right. And current, you don't need to flip your thumb, right? Because current is always positive. So this guy should feel force to the right. If I turn it on now, so let's try that, okay? So you will see it's going to go that way. Okay, now I'm going to turn it on. Right? You see that it moves in that way because there's a force. I can't even put it back, right? See, if I try to put it back, it's still going to go that way because there's a force from the magnetic field on this wire as predicted by the right-hand rule, this theory, which is a conclusion from that theory, right? So that's how I turn it off, comes back, no force at all, okay? So that's how we verify this theory, right? Again, how do I believe the theory? Do an experiment, right? Compare the experiment with the predictions. If they agree, I believe in that theory. And then this is what we did. We did verify this theory, okay? So this is the first thing I want to do with you. Now I'm going to remove this so that it gets out of your way. I want you to see the whiteboard, okay? All right, so last time we discussed this theory, right, which is conclusion from that theory, the force from the magnetic field on a straight current, which carries a straight conductor, which carries a current, okay. Now we're going to discuss the real source of magnetic field. What is the real source of magnetic field? What causes all these magnets to get its own magnetic field? Okay. So because there's no isolated north pole or south pole, right? The theory is going to be totally different from the electric charge, right? If people ask me or anyone, what is the source of electric field? How do you create an electric field? You would say, well, easy. Just grab some positive charge or grab some negative charge, right? So the source of the electric field is just going to be these charges, right? And they are isolated. Positive and negative charges to create a electric field, right? So, but what is the real source of magnetic field, right? Because remember, there's no isolated north pole or south pole, right? So you can't say that the real source of magnetic field is this like isolated north pole or south pole. We don't have that. Then what is the real source? So it was a puzzle for physicists in the 18th century, okay? And eventually this Danish physicist, Ørsted, during a lecture, okay, he noticed he was not really trying to figure out the real source of the magnetic field. He was just doing an experiment. He was just setting up an experiment for electric current, right? You just set a battery, some wires and resistors, and he was doing an experiment on that, like Ohm's law stuff. And then he placed the compass near the circuit, okay, by mistake. Maybe he just forgot to remove that compass, okay? And then he realized that every time he switched the battery on and off, then there's a current in this circuit. Then actually the compass is going to respond to that. So the compass is going to be deflected if the current is on and off, okay? And then it was weird to him, okay? Then 3 months later, he did a lot of work on it, and then he published his findings. He showed that the electric current is the real source of magnetic field. Okay, so that means in order to create magnetic field, you actually just need to create electric current. Okay, so any electric current is going to create a magnetic field. So that's a conclusion, right? Slide 8, lecture 18. And a current is just nothing but moving charges in a conductor, right? What is the real source of magnetic field? Moving charges. So if the electric charges are moving, okay, they will create magnetic field around them, okay? Again, by the first look, it's really weird, right? Electric charge. Yeah, electric charge creates electric field, I know that. Any electric charge is going to create electric field all around it. But now you're telling me when this guy is moving, it creates magnetic field around it, okay? So that's really weird. Again, it's because you don't have experience. You don't have direct experience with these guys. Like people always think that electric field and magnetic field, they are totally independent. They have nothing to do with each other. But we have already seen a lot of hints that there are a lot of connections between them. And then if you think about it, if you use the relation between electric charge and electric field, okay, so actually it's not a surprise anymore. It's actually the only way to make a complete theory, right? So think about it. Electric charge creates electric field, okay? No doubt, we know that. And then if you place another charge in this electric field, the test charge, it's going to feel an electric field. It's going to feel a force from an electric charge, right? So electric charge is the source of electric field, but the electric charge can also feel the electric force from a pre-existing electric field, okay? Sounds a little bit confusing, but that's the connection between electric charge and the electric force and the electric field, okay? Then we already learned that moving electric charge, they will feel a force from another magnetic field. So compared to the relation between electric charge and electric field, so it's actually not a surprise that electric charge can create their own magnetic field, right? Think about it compared to electric charge and electric field. Electric charge can create electric field. Electric charge can also feel a force from another electric field, okay? Complete theory. Electric charge is the only guy you need, right? It's going to create its own electric field. It can feel electric force from another electric field created by another electric charge, right? And then moving electric charge is also the only thing you need for magnetic field, because moving electric charge is the source of magnetic field. It can feel the magnetic force from another magnetic field. Okay, so it's a complete theory for electric field and magnetic field. So you don't need any magnetic monopoles to make a theory for magnetic field. The only thing you need is electric charge. So electric field and magnetic field, they're both created by electric charge. But the difference is that in order to create an electric field, you only need an electric charge. Doesn't matter if it's moving or not. It's not moving, it creates electric field. It is moving, it also creates electric field. But when the electric charge is moving, it's also going to create magnetic field around it. Okay, so the only thing you need to create electric field and magnetic field is an electric charge. The only difference is that in order to create a magnetic field, you have to have it move. Okay, if it's not moving, so sitting here, it's going to create electric field only. But if this charge is moving, it will create both. It has its own electric field. It's also going to create magnetic field around it. Okay, so that's a complete theory for electric and magnetic field. Okay, again, you think it's weird because you always think that electric field and magnetic field, they are independent, they're not connected, but actually they are connected. Okay, it's because we are stupid. We discovered electric field and magnetic field separately. We thought they are two different fields. Actually, they are not. They're just two different components for the same field. Now we call E and M field. Okay? If this is weird to you, think about this, right? Before Einstein, people think space and time are independent. Space is space, time is time, right? They're not connected, right? Space has 3 coordinates, time has 1 coordinate. And Einstein realized, no, they are actually one thing, okay? So in this, we live in a 4-dimensional space-time, okay? So time is just another component in this space-time. You shouldn't separate space and time. You should combine them and always use this 4-dimensional vector to do physics in space-time. So now we call it space-time. We don't call it space and time, right? So this is the same thing for electric field and magnetic field, okay? So after all this work, we realized that, okay, it's because we are stupid. We discovered electric field and magnetic field independently. We thought they are 2 independent fields, but actually they are not. They are 2 different components of the same field. Now we call E and M field. So of course, it only needs one source, electric charge, right? It doesn't need anything like a magnetic monopole, okay? So this is the theory for electric field and magnetic field. Of course, as I say, if anyone discovers magnetic monopole in the future, it's gonna, all the theory is gonna be rewritten, right? But so far, this is the complete theory we have for E and M, okay? All right? So that's the real source of magnetic field. Then, if you want to make predictions, if you want to do calculations, if you want to do experiments, you need a law. You need to also find the law. Okay, so this law was discovered. Okay, so it's a very complicated law. Okay, so in order to find the, you can see it's on slide 9. Okay, so in order to find the magnetic field of one moving charge, you have to use this vector equation. This is called Biot-Savart law. Okay, mu naught. Okay, it's called permeability of free space or magnetic constant. This is like a constant. It's pretty much like the Ke we have been using for electric field, right? Divide by 4 pi, and then charge, the speed of the velocity of the charge, which is a vector. And then this r hat is the unit vector you draw from the charge to the point you want to calculate, and divided by this r squared. Okay? So if you look at the image on this slide, you see the definition of r. Because when some charge is moving, it creates a magnetic field all around it, right? Any point. Okay? So you have to, if you want to find the magnetic field created by this moving charge, you have to do that for each point. Well, it is a lot of work, but this is the theory, right? So the charge is moving, say in this picture, to the right. You want to find a magnetic field right at this instant, right at this black dot, okay? So that's the theory you're going to use, right? You will have a v vector for this moving charge to the right. You will also draw a r vector from the charge to the point you want to evaluate. So that's these 2 vectors. And then this is the magnitude, and you square that, and this is a constant. Okay. So this is a very complicated theory. And then think about it, right? And then if you really want to use this theory to calculate the magnetic field created by a moving charge, it's going to be very hard. right? Because next second, it's moving, right? Next second is going to be at a different location. So everything changes, right? V might be a constant, but this R is going to change, right? So the magnetic field created by moving charge, if you really want to calculate that, it's going to be really hard, okay? So but we're not going to really do that. We're not going to really use this theory to calculate the magnetic field created by one single moving charge in this class, okay? So don't worry about this equation, but this is a fundamental theory. And then if you, let's move on to slide 10. Then if you have a conductor, right, then all the charges are moving in this conductor, right? A conductor has a current, say the conductor has a current. The current is nothing but a lot of charges moving in the conductor. So, and then each charge is going to create its own magnetic field. And then at the end, the net result is that this conductor is going to create its own magnetic field around it, right? So you can derive that pretty much like you derive this equation from that equation. We didn't derive that, we just went and have to use that. You can also derive the equation to calculate the magnetic field created by a straight wire, okay? The magnetic field created by straight wire using this fundamental theory, so which is the equation on slide 10. So this is going to be an integral, okay? I is the current, dl is the infinitesimal element peak on this conductor. You can take a look at the image on slide 10. And then this is r hat, the unit vector in the r direction, and this is r squared. So again, even if I have this theory, right, calculating the magnetic field created by a straight wire, it's still going to be very complicated. So we're not going to really do that here. So we're not going to really use these two equations to calculate anything. So we don't even need to remember them. I'm not going to even give you these two equations because we will not use these two equations to calculate anything in this class. Okay, because this is the intro level class. What we will do is that we're just going to take a look at some very special cases. Okay, very special cases. So we're just going to go ahead and use the conclusion. Okay, so these special cases, they can be derived to use this theory, but we're not going to derive that. We're just going to use the conclusion. Okay, so the first special case is a very long and straight wire, right? So, and this is a special case, this is a simple case. So you can derive the magnetic field from created by this straight wire. So you're going to use this theory to derive that, but we're not going to derive that. We're not going to derive that, okay? The conclusion is this. It's very interesting. A straight wire, so if you look at the image on slide 11, a straight wire carrying a current, like say in this way, right? It's going to create a magnetic field all around it. How do you draw the magnetic field lines created by a straight wire? It's going to be a bunch of concentric circles centered on the conductor, okay? So you look at the image on slide 11, okay? So if you have a straight wire, so I'm just going to use this rod, okay? So this is a straight wire. This guy has a current in that way. It's going to create a magnetic field out of around it. Okay. Again, it's weird, right? But that's the theory. That's the theory. Okay. And again, we can do an experiment to test this theory. Okay. So that's how I believe a theory. Okay. And then the magnet. How do we draw the magnetic field? Okay. It's very weird. The magnetic field lines are a bunch of circles around it and centered on this conductor. Okay. So you can also look at the image on slide 11, okay? But then, okay, even if you tell me the electric field, magnetic field is going to be around it, okay, circles centered on this conductor, but there's still two options for these circles, right? The circles can go this way or that way, right? Even if you tell me they are circles, right? How do I know the magnetic field created by this straight wire carrying current, okay? It's going to go this way or that way, okay? So we still use, again, first of all, everything can be derived using this theory. So we didn't derive that. So you just you feel like I'm just throwing facts at you, okay? But they can be derived. And then we still use right-handed rule to determine the direction, right? We determine if it's to go this way or that way, okay? What is this right-hand rule? It's a shortcut. So it's a shortcut to help us figure out the direction without using this theory, right? Without using this theory. It is a conclusion from the theory, but we don't use the theory in this class. So that's what you do. You're going to grab the conductor using your right hand, okay, like this, okay? And then you're going to make sure that your thumb is in the direction of the conductor. Then your four fingers, okay, are telling you the direction of the magnetic field lines. So in this case, if there's a current going in that direction and this conductor, imagine this is a conductor, it's connected to some battery or something. If there's a current going that way, I'm going to grab them using my right hand, not my left hand, right? Put my thumb in the direction of the current. So now I see that my four fingers in that way. So it's telling me the circles must go this way instead of the other way, okay? Okay? And then this is a little bit hard to see and draw, right? So what we do is this, right? If I draw a view like this, right? Look at this, okay? So if I place it this way, the current is going that way. So I would draw a view on the piece of paper. So you will see a current going into the page, right? So remember the current is going that way. Now I'm going to rotate it 90 degrees. So the current is going into the page. You're going to see a current going that way. So that's why I don't need to draw this conductor, right? Because this is my view if I look at it from this side. Now I just see a current going into the page, right? So in that case, I'm just going to grab the conductor using my right hand and put my thumb in the direction of the current into the page. So now you see my four fingers in that way. So I should see circles going around it this way, not the other way, right? So I would see the circles going around it clockwise. So that's how I would draw the magnetic field lines of a straight current on a piece of paper, right? I draw it this way. This is a view from the one end of the conductor, and then the magnetic field lines are going to go clockwise, right? You can draw as many circles as you want, right? But that's the magnetic field created by straight wire. Again, very weird, right? But that's because we never have direct experience with these things. We never do things like this in my life, right? Newton's law is very intuitive because we're familiar with this. We're familiar with velocity, acceleration, forces, right? Things moving. But we don't have direct experience with this. And then the magnetic field, they're even invisible, okay? So that's why it's very weird to us. But again, as I said, we will do some experiments to test the theory so we can believe the theory, okay? So that's how you find the direction, right? So say if the other case, if I draw connecting, I still have this wire, right? Now I have the current going in this direction, not that direction, but I still want to draw a view from this end, so on a piece of paper. So if the current is going this way, I rotate it 90 degrees. I want to draw a view from this end, so I will see the current coming out, right? So I would draw it this way. I would draw, this is the view for the conductor. I see a current coming out. This is the previous one. Then what is the direction of the magnetic field created by this straight wire? Grab this straight wire using your right hand. Put your thumb in the direction of the current. So now the current is going that way out of the page, so I would grab it this way. My thumb is going that way, so that's the current. Now my four fingers are in this direction, right? So that means the circles are going to go counterclockwise instead of clockwise, okay? So I would draw it this way. So this is the magnetic field created by this wire. Okay, it's very weird because we don't have direct experience with these guys. Okay, but we will do experiment. We'll do some experiments to test this theory. So that's the direction. Okay, you grab the conductor, a straight conductor, using your right hand. Put your thumb in the direction of the current. Your 4 fingers are in the direction of the magnetic field lines. Okay. Now the magnitude can also be calculated using this theory, but we're not going to derive it here. We're just going to go ahead and use the conclusion, which is going to be on slide 12. Okay, so that's going to be mu naught I divided by 2 pi. What is the symbol I'm using? D. Okay, so in this case, you see that what numbers do you need if you want to calculate the magnetic field created by a straight wire? Mu naught is this constant, right? What is this mu naught? Well, the value is on slide 9, right? So this mu naught is a constant 4 pi times 10 to the negative 7. Okay, very small number. Unit is Tesla times meters over amp. Okay. So you need this mu naught is a constant. It's like the Ke we have been using for electric field, right? That's why it's called a magnetic constant. I is the, you definitely need the current, right? Because you are calculating the magnetic field created by this current. And then 2 pi, well, constant. D, what is D? D is the distance from the point, right? Because at different locations, the magnetic field is going to be different, right? It's not a uniform magnetic. For example, if I want to find the magnetic field at this point, this is going to be the D I use, right? If I want to find the magnetic field at this point. And also, if I want to find the magnetic field at this point, this is going to be the D I use. So actually it goes down with the distance, which makes sense, right? Imagine if I want to calculate the magnetic field very, very far away from this guy, right? Very, very far away from this guy. Of course, I'm going to get a very small number, right? So that's why it goes down with the distance. Okay, so that's the magnetic field created by a straight wire. Okay, now let's. I want you to solve the problem on slide 13. Okay, so just to practice this theory. So this is very easy. You just plug numbers in. I want to use this problem to show you that how weak this magnetic field is. Okay. A long wire carries a current. What current is required in the long wire in order to create a 1 Tesla magnetic field at a point 1 centimeter from the wire? Okay. So that means you just use this equation, right? You want to create a 1 Tesla magnetic field. So you already know the magnetic field you want. Okay. That's going to be 1 Tesla. And the mu naught is constant. You want to find how strong the current needed in order to create a 1 Tesla magnetic field 1 centimeter from the wire. Okay, so the distance is also given, right? I want to make sure that I want to make a magnetic field around a straight wire 1 Tesla at 1 centimeter from the wire. So which is very, very close to the wire, right? Okay, you put numbers in to find the I. Okay. Right, so pause the video, do the math, okay, see if you can get the right answer. Okay, at the end you will get this answer, right? And this is a huge, ridiculous current, right? It's like in the order of 10 to the 4th. So in order to create a 1 Tesla magnetic field 1 centimeter from the wire, it's already very, very close, right? You're going to need such a huge current. So this is not very practical, right? Even if I know that a straight wire is going to create a magnetic field, but if I want to use that fact to create some magnetic field for experiment, instead of using this permanent magnet, this is not very practical, right? You see that if I want to create a 1 Tesla magnetic field, I would need such a huge current. First of all, it's very dangerous, right? Secondly, it's going to cause a lot of heat in these wires, right? So these wires, they're going to melt very soon, okay? So even though this is how you create a current, a magnetic field using current, this is not very practical. But we will learn a practical way to create magnetic field using a current, okay, in real life. But before that, let's take a look at a very classical problem in this part. So that's the magnetic force between two parallel conductors, okay? So what is this problem? The problem is this. If you place two wires, parallel wires together, okay, and then there must be a magnetic force between them, okay? So let's draw it out. So slide 14. Say if there are two straight wires, so the first one, so they carry current, right? But in the same direction, so this is I1, this is I2. Two different wires, but they both carry some current, right? So they may be connected to a barrier or something, well, I don't care. But they each carry current, we call I1, I2, they are in the same direction. So there's always a magnetic force between them. Why? Okay, let's do that. Okay, let's take a look at it. Because think about this. Think about what we just learned. A magnetic field, a straight wire carries a current. It creates a magnetic field all around it. Okay, so that means if you look at I1, only I1, right? So let's do this. I'm going to erase all this. So I1 is a straight wire. It carries current. So of course it's going to create magnetic field around it. That's what we just learned, right? If this guy is a straight wire, it carries current that way, it will create a magnetic field all around it. How do I determine the magnetic field? You're going to grab the wire using your right hand, right? And then put your thumb in the direction of the current, then your forefinger in the direction of the magnetic field. So it's going to have a magnetic field this way. Okay, but if I want to draw it on a piece of paper, that's hard for me to draw, right? How do I draw circles this way on a piece of paper? So we don't draw these circles. We use dots and crosses to help us visualize the magnetic field. How do we do that? Think about it, right? Now I just figured out that the magnetic field lines, they're going to go this way around this wire. So for all the points above this wire, only on this plane, you're going to see all these magnetic field lines coming out, right? So I'm talking about like a point here, all these points above this wire, magnetic field coming out, right? So that means I don't need to draw these circles. I just draw some dots above I1 to tell myself these arrows, these field lines, they're going to go out of the page above this wire. Then what about the points below this wire? Again, the field lines are going this way. So if I pick a point here, what is the direction of the lines? Right at this point, going in. Right at this point, going in. Right at this point, going in. Okay? So I can just draw crosses below I1 to represent the magnetic field created by I1. It's not uniform, right? Because it goes down with the distance. Okay? So instead of drawing these circles, if I draw the whole wire, and then I'm only interested in the magnetic field on this plane, I would just draw dots and circles dots and crosses to help me visualize the magnetic field, right? So that means the magnetic field around this guy is going to go this way. Okay? So that's easy for me to figure out the force from I1 or I2, right? Because now you see that I1 creates magnetic field all around it. I2 is in this region. And I2 doesn't even know I1 exists or not, right? I2 doesn't know where I1 is. I2 is here. In this region, what does I2 feel? I2 feels, well, there's a magnetic field in this region into the page, right? That's what I2 feels, okay? And then if you place I2 in the magnetic field into the page, I2 is going to feel a force from that magnetic field, right? Because that's what we learned last time. Magnetic field always has a force on a conductor which carries current, because this conductor is just nothing, this current is nothing but a lot of charges moving in that direction, right? And each charge is going to feel a force from this magnetic field. And you add all these forces together, that's going to be the net force on this conductor, right? So that's how we figure out, that's why there's a force between two parallel conductors if you put them together. Because the first conductor is going to create magnetic field around it, all around it, okay? And the second conductor, it's going to feel the magnetic field. It doesn't really know if I1 exists or not. It just feels there's a magnetic field around itself, right? So in this case, what would be the direction of the force from this magnetic field? We call it B1. It's created by I1, right? What is the magnetic force from B1 on I2? You're going to use this theory, right? So you're going to do I toward B, I toward B, right? So this is a different theory. This is a theory we learned last time. So the force from B1 on I2 is going to be up. So 1 on 2, I'm going to call this force 1 on 2. All right? So that's why if you put two parallel conductors, both of them carry current, there's always a force between them, okay? So how do I figure out that force? You use these two different theories. The first theory is this, is the theory we learned today. A straight wire carries current. It always creates magnetic field around it, always. Okay? How do you find the magnetic field? You grab it. You grab it. Your thumb is in the your thumb in the direction of current. Your 4 fingers are going to tell you how these circles go. Okay? Then we don't draw these circles on a piece of paper. We use dots and crosses to help us visualize the magnetic field. Then the second wire is going to feel the magnetic field created by the first wire. Then you use this theory. It's also called right-hand rule, okay? They are the same name, they have the same name, but they're different rules, okay? We call them both right-hand rule because we use the right hand. Now you don't grab anything, you do I toward B, okay? So a lot of people, when we have reached this part, they're confused by these two right-hand rules. They're different right-hand rules. We call them both right-hand rules, but they're different. This thing, you grab it because you want to find the magnetic field created by current, okay? This, you already know there is a magnetic field in that region. You place a current there. You want to find the force on the current. You don't grab anything. You do I toward B, okay? So, okay, I'm going to stop here and see how it went.